So, a very warm welcome to everyone. Welcome to this interview series called Cosmic Vartalap. Today, it is a true pleasure for me and my fellow interviewer to be able to get a chance to interview one of our teachers and an excellent astronomer.
And the astronomer we have today with us for the interview is Dr. Manoneeta Chakraborty. She did her B.Sc from University of Calcutta and later on went to Tata Institute of Fundamental Research, Mumbai, for her M.Sc and Ph.D. Her postdoc is from Sabancı University, Turkey, and she is currently a professor here at IIT Indore, which is another reason why Branjali and I are so excited to have with us Professor Manoneeta Chakraborty.
Thank you both of you for inviting me here. It's a very great pleasure to be here and interacting with you, both of you.
Let's just dive right into the questions. Let's just make things way more interesting. Okay. So I know, ma'am, you have probably answered this question like a million times already, but still I would like to ask it again. So how would you like to summarize your research work in order to pursue other students to, inspire other students to pursue the same?
Sure. So my work basically involves compact stars, particularly to exotic kinds of stars, black holes and neutron stars. So just for people who don't know about them, these objects are created when stars having masses greater than 8 solar masses dies and leaves this remnant. Now, why these objects are interesting? Because they are very, very, very dense. So imagine the entire mass of a sun compactified into the size of Indore. So the densities will be super high, and consequently what happens is that the gravity around them reaches extremely strong values, what we call strong field regime. What that means is we can test the various theories of gravity, for example, Einstein's theory of gravity or the alternate other theories of gravity around these compact objects to unprecedented level compared to anywhere around the universe. Also, among these two classes of objects are the neutron stars, and neutron stars have this very interesting property that they are so dense that the density inside their core reaches ultra strong values. What I mean by that is the density becomes even higher than the density inside a nucleus, which is the most densest thing that we know of, right? So that means that the matter inside there can exist in conditions which is even beyond the nuclear conditions, and they can exist in some exotic phases. We can see free quarks, pasta phases, and so on and so forth. And understanding the nature of this matter will unveil the physics that happens at this extreme conditions. So what I do is me and my group studies this kind of objects, black holes and neutron stars, through observations using various kinds of telescopes, starting from the radio to the X-ray bands. And we look at the signatures, the imprints they make on their surroundings. So they make signatures of the strong gravity, they make signatures of this ultra strong exotic phase of matter that is there at the core of the neutron star. And also, one thing I didn't say is the neutron star is also very strongly magnetic. So the magnetic field that is typically there for, let's say, the average neutron star is about orders and orders of magnitude higher than the strongest magnetic field that you can get in your standard labs on Earth. So that means that the physics of ultra-strong magnetic field can also be tested close to these objects. This particular class of object having strong magnetic fields are called pulsars. And what we do is using telescopes like the upgraded giant meter wave radio telescope in radio and AstroSat in X-rays and many other missions, we look at the emission that is coming from nearby these objects, which has imprints of all this exotic fields that I talked about. And looking at the data, we test it against the existing theoretical models and try to infer about the properties of these objects and the undergoing physics around it.
Thank you, ma'am. It seems interesting. I mean, studying rare objects is exciting on its own, and then you get to test theories using that. So Thank you so much for the answer.
At first, I used to think, okay, Manoneeta ma'am is very exciting just because of her nature, right? But later on, I realized that, I mean, how excited a person actually is doesn't exactly completely depend on the upbringing and all, but it also depends on the thing that the person is pursuing. And I guess Manoneeta ma'am is so much excited only because of the exciting stuff that she studies.
I am glad that you find these subjects exciting because they are very exciting to me.
Yes. Right. Okay, so let's move on to the second question. Right. So you have 19 research papers under your name, right? Right. With the most recent one being revisiting the subpulse drifting phenomena in a pulsar, right? So what is this paper all about, and I mean, what are the results that you and your team received?
Yeah, so I would love to talk about that. So this work, which is led by my PhD student Parul, involves pulsars, the object I just mentioned. So pulsars are nature's premier laboratories for testing extreme physics, the physics of extreme gravity and the physics of extreme magnetic fields. But in spite of them being discovered 50 years ago, their emission mechanism is still not completely understood. And there are various tools or observational signatures to probe this emission mechanism. And one such mechanism is called the subpulse drifting. What is subpulse drifting? It basically means the substructures that are there within the main pulse. A pulsar has a strong pulse. So whatever the substructures are there within the main pulse of a pulsar, these are called subpulses. They show systematic drifts with phase, pulse phase. And this phenomenon is called subpulse drifting, and it can provide a key understanding of the physics that is going inside the pulsar magnetosphere, and thereby giving us a tool to probe the pulsar emission mechanism. So what we did to understand this subpulse drifting mechanism even further, we looked at this pulsar PSR J1822 minus 2256 using UGMRT, the GMRT telescope that we have in Pune. Now, GMRT, it's anyway a very excellent telescope, but now what we have is it's upgraded, and that gives us a wide bandwidth. So that means we can look at whatever the properties of the pulsar over a wide frequency range and with very high sensitivity. So we precisely did that, and we looked at this subpulse drifting phenomenon from this particular pulsar. And what we saw that there are obviously drifting happening for this pulsar, subpulse drifting, but the drifting behavior is also changing. And we discovered there are 4 different distinct drifting behavior with very previously undiscovered new features. And also because of the wide band capability of GMRT, we looked at the frequency evolution of the subpulse drifting. So we obtained how the subpulse drifting changes with different energies. What that gave us information about, first of all, why the different drifting mode is happening. So we associated the different mode with different emission heights in the pulsar magnetosphere. And also we showed that the properties of the drifting modes can be explained using what we call the spark model, which basically says that inside the pulsar magnetosphere, there is a carousel like the carousel we see in the fairs. There is a carousel-like pattern where different sparks are happening and which are giving rise to this different slowly drifting behavior. So we explained the 4 drifting patterns that we saw using this model, and we showed that this is happening from different heights of the magnetosphere. So our results thus provide vital clue towards understanding the pulsar emission mechanism, and this helps towards refining this spark model because it gives its corresponding emission spectrum and emission height mapping with the different drifting modes. Is it understandable?
I mean, yes, to some extent it actually was, because I have read a couple of research papers on pulsars. So yes, I could understand a couple of the terms that you use, right? But yes, I mean, your research areas are really vast, honestly.
Ma'am, when was this research paper published, the one that you talked about just now?
It's in 2022. Actually, it was accepted in 2021, but the final publishing happened in 2022, January.
I mean, you remember the name of the pulsar, such a long name.
Yes. Yeah, I spent a lot of time with it. My student did it more, but yeah.
So, what is B.Sc working on, by the way? B.Sc?
B.Sc has just joined, so he will start working on XRBs, but on astrosat data. By the way, this probably requires a little bit of discussion with him, but yeah, basically on low mass X-ray binaries using astrosat data. But he did his M.Sc project on something called ULX pulsars. So these are certain kind of pulsars which exceeds their Eddington limit.
Okay.
But still, they are pulsars, and that have certain consequences for the way the acceleration mechanism can happen inside the pulsar magnetosphere, and also has consequences for the model of ULXs, because ULXs are the primary candidates of intermediate mass black holes, but we are finding a section, at least a population of ULXs as pulsars. So he worked on the first galactic ULX pulsar that was detected.
So I'll move on to next question now. So I mean, of course, we'll discuss about like the details and nitty-gritties of the research work, but this psychological aspect is also quite important. So I would like to ask, what was the most difficult part about transitioning from being a research scholar to being a professor for you?
Okay. It's a very interesting question, and yeah, it's a significant step. So the first thing that I will say is the multitasking and time management, because when you are a research scholar, you are just concentrated on your own research, and that's your whole world. But when you are a faculty, by the way, I'm not a professor, but I get what you are saying. So when you are a faculty, you have various aspects to your job. Like research is a part, but then again, you have to deal with your students, you have to teach classes, you have to do certain administrative job, and this all combined, you have to do a lot of time management and multitasking. So that takes a time to get adjusted to, because all you want to do is concentrate on your research, because there is something very exciting to be discovered. That's always the feeling. Yeah, that's what I would say that was the most difficult part. Yeah.
Along the same lines, I mean, can you like explain what was the most difficult part about transitioning from being like a student, a college student, to being a research scholar? I mean, what was the most difficult part about that also?
Yes. Okay, that's also a very exciting and very important question, and I always tell this to my students, because when you are in college, what happens is that you are going to classes, and whatever you have to do is very defined, right? You have to solve certain problems. The answer to the problems are defined. The teacher knows the problem, and if you are unable to get to the answer, there is a teacher to help you, with who knows the solution. But when you are going to research, the whole point of research is you are traversing to some area which is unknown, right? That's what research is, because you are discovering something for the first time, however small or big it is. So often what happens is that it takes a time for anyone to get adjusted to this idea that what you are now trying to achieve doesn't have a known definite answer. And there is a lot of uncertainty, a lot of failure, and not even your teacher knows the answer to it. Not the absolute answer to it. Maybe he or she may know the pathway to it, but definitely not the answer. If he or she knows the answer, that's not research. That's not a new research.
Yeah. Right, absolutely.
Yeah, that completely makes sense. Yes, that's not a research. If your teacher knows the answer to that question. So, I mean, see, astronomy is so vast. I mean, when a person's puts his first step into astronomy, the first question that comes to his or her mind is how important it is to, decide a particular area in astronomy when you are doing your master's. And when you took that first step, when you had so many options to explore, then you must have come across so many different areas of astronomy. And what great impact did your PhD have on the topic that you chose during your M.Sc?
That's a very important question, Aryan. So obviously, I mean, it helps if you already know which area you want to go, because you can start building towards it, and you can do research projects in that area, which helps, let's say, finding the next job, be it PhD, be it postdoc, be it the next master's. But I don't think it's absolutely necessary to know particularly at, let's say, a bachelor's or a master's stage. Firstly, a prior experience in research in a particular field definitely equips us with certain tools. But when you are doing a PhD, it's so deep, so vast. You have to still learn a lot of new things. So it's only an incremental change that you will have if you are not in that field to begin with. And secondly, in astronomy, we tend to focus on our own very, 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 very small sub areas. But what happens if you keep your mind a little bit broad, you will see that whatever the skills you develop in any branch of astronomy, those skills are quite transferable to many, many different areas across all fields in astronomy, and I would say even physics, but particularly astronomy. So techniques, the physics, the connections between various areas of physics. So those are very transferable. So if you are clever, it doesn't matter which field you are doing your master's or your bachelor's in. And if you develop your basics and your skills well, that would be very well applicable to other areas that you later on want to explore. And I believe that, at a young age, it's very okay to explore, because how else will you know what else is there? Because astronomy has a wide variety of very exciting topics sitting there just for you waiting.
Absolutely, yeah.
Thanks for asking that question, and seriously took off some burden off of the shoulder. I mean, like, everyone is thinking like project is important. Yeah, it is important, but then at the same time, we think that this project is going to define our path in future. So we all, I think, at least I thought about.
No, we all
necessarily. No, of course, I won't deny it helps a little bit your application, but definitely that doesn't necessarily stop you from going to any other field. For example, I know a lot of people who have specializations during their masters in ConMat, but they have ended up going to astronomy. So, yeah, it's possible.
Okay, so now moving on to the exciting part. I mean, what was the most exciting, what is the most exciting aspect of your research? And along the same lines, what is the most difficult aspect about your research?
Okay, so I will start with the difficult one, because there should be a silver lining. And the difficult one is, it's true for all research, the one that I will say, it may be a little bit vague. So see, I work with observational data, and I will work on, different kinds of objects which are very unpredictable, and a large quantity of data. So what happens is that often there will be a huge traces of period where I have to investigate and mine through a large amount of data, large amount of techniques, without in some immediate results. And there will be lots of phases of null results, lots of phases of redoing, lots of phases of, let's say, what we call dull phases. And often you will find it it's difficult to keep your motivation up at the same level, even though you know what's the final site, you know what's your end game, but still, so that becomes the difficult part. So at that point of time, to persevere and still, not be distracted from your path, that's would be the most difficult part. And on the same lines, the most exciting part is twofold. One is when this dull phase ends and you get the first glimpse of the result. That is something you yourself are getting for the first time, not just for you, but for anyone in the universe. So no other excitement can come very close to that. Okay, I mean, maybe that's a bit of a hyperbole, but
No, ma'am,
yeah.
literally gave goosebumps. I mean, I had
Really,
goosebumps.
yes.
Yeah, and the second part to the excitement is I also like one thing which excites me very much is discussing my ideas with my peers and students. And when you get to resonate with somebody or get some new ideas, that's also pretty exciting.
His resonance works everywhere. Equally important as in design. Oh, resonance is amazing. And actually, ma'am, we both, and in fact, all the viewers who will be watching this interview will be able to feel whatever you said in this particular question. I mean, I really had goosebumps, just like Pranjali. It was like a movie scene. I mean, all we needed was Akshay Kumar.
Yeah.
So, okay, the next question, I was really a bit skeptical about this one, okay? Because I thought, okay, this might raise some controversies, but I guess you all are okay with it. And moreover, we can edit it if we want to. But see, you have done your PhD in India, right? And you did your postdoc from Turkey. Moreover, you have had interactions with the people from different countries, right? So, how different do you feel is the experience of, the research in India and research in other countries?
That's a good question. I will make an unpopular opinion that is, at the very base academic level, there is not a very drastic difference. Okay. There is some, but not a drastic one, obviously. Resources are more readily available abroad at a typical, well-to-do university, well-endowed university, I mean. And also, one particular thing I have enjoyed is the exposure. Typically, outside, you get a little bit more exposure to all the research that is going on all around, because, but the commute is easier. That's the bare bones of it. Also, the one slightly non-academic thing that I have liked is typically there is a healthier work-life balance there. So that's one thing I have found as a strong pro. But in general, I have found there is a bit of both both in India and outside, and there are small pockets everywhere, including India, where lots of good research is being done. I have felt that it often depends on the individual groups themselves than the complete university or complete institutes. That's the academic structure, right? So yeah, that's till now what I have felt.
By work-life balance, you mean they let you go early, or
yes? No, the thing that you will see there is they have relatively more defined working hours, but you will not see anyone slacking during that hours. So they will come at 10 and go away at 6, but they are very efficiently working during that time. Whereas in India, it's typically longer, but that's why we tend to have teas and other things in between too many times.
Not going to say anything regarding the tea.
Sorry? No, tea is always welcome. Tea and coffee are the fuel of doing academic research. So
Wherever I go, professors tell me, if you have to complete your PhD or whatever, you either have to drink tea or you either have to drink coffee. That's the only way.
I wholeheartedly agree with that statement. Though not biasing anyone, but from my perspective, I agree.
So, moving
Because,
on from.
yeah.
No, sure, go ahead.
No, I just wanted to say that often it's long nights, long tiring days. So tea, coffee helps in that.
It does, yeah.
So moving on from the exciting part, maybe this is also exciting, I don't know, but when I entered astronomy, I had those beautiful pictures in mind, looking through optical telescopes as such. But when you come into astronomy and you look at the technical part behind, the tools and techniques used behind all those beautiful pictures, then you come to realize, okay, it's much more than that. So what are the tools and techniques used by you in your research work?
Oh yes, that's a very good question, and I use a lot of tools. So I use radio data and X-ray data. There are different kind of tools I use for them. So the first thing I would say is a huge part, particularly for us observers, is when you get the data from the detector, it's raw data, right? So a huge part is reducing the data to some scientific data, what we call. And this requires a lot of calibrations. For radio, it means image processing and calibration. That involves a lot of ideas of Fourier transforms and noise reduction and so on and so forth. For X-rays, also some similar concepts are there. Lot of ideas of how detectors work, and from there onwards, how raw data can be processed, recalibrated, filtered, and those kind of complex, slightly advanced procedures, which I will not go into. But that's I wanted to mention is because when we observers have the data, we tend to forget how important detector is, how important our antenna is, and it's important to understand that as well. As important as understanding the neutron star or the black hole, because only when you understand your instrument, then only you can reliably infer about your object. The second thing what I do is my objects, the compact objects, they are very variable. Their emission very fast with time. So main focus of my work often involves with understanding this time variability, or what we call time series analysis. So it involves Fourier transform, it involves searching for periodicities, long-term predictions, and all those kind of techniques. And apart from that, we also look at the different kind of emissions, as I mentioned, that are coming from this compact object. And in order to infer and understand the physics, which I mentioned before, you need to try out the different theoretical models, right? And that involves various statistical model fitting and inference parameter estimation. So these are the kind of techniques I use, to name a few.
Lots of techniques. I mean, is it like a single person's work, or like you kind of form a team or something?
Well, definitely I have a few students, so that's my team. But even one single student has to deal with at least some of, if not all, some of these techniques I mentioned.
And can a person master these techniques in a year or two, or
A single person looks, that feels quite impossible.
No, not all, but you have to define your objective, and depending upon the objective, you define what are the techniques that you would require to reach that objective. Okay, so if you have 1 or 2 years to reach a certain objective, which is, let's say, I want to understand what is the, let's say, pulsation properties of XYZ object, then you look for all those techniques that are required to do that. So if you need X-rays, then you learn X-ray data reduction. Then for pulsation, you need a little bit of time and frequency phase analysis. So you learn that. So that's how it works. And on the way, there are some common things which kind of applicable across. For example, model fitting, parameter testing, you must have done in some other areas as well, right? In your experimental labs.
I'll definitely show this video to my cousins who are interested in astronomy. Should get a glimpse on, what's behind the curtain, those statistical words. Then they'll get to know how much interesting it is.
No, don't discourage anyone because, as I said,
they will still love astronomy.
As I said, this is worth the light at the end of the tunnel.
Yeah.
And that feeling nobody can replace,
Yes, absolutely. Right. So we as interviewers, right? So we have this advantage of asking you a personal question. So I'm going to make use of this benefit right now, and I'm going to ask you, being an astronomer, and more than that, being a science enthusiast, what is your take on the theory of multiverse?
It's a theory and a very interesting one. I like it, but as a scientist, I have to say that till now there hasn't been any confirmed proof of it, so it's still a theory. But what I read a story long back, a science fiction story, which kind of said things like there are different multiverses, and each of this multiverse, the fundamental constants that shape our universe are slightly different. So that means the laws of physics are slightly different in each of the multiverse. And that was a very interesting, scenario to imagine. So those are some fun experiments we would like to do with multiverses. But yeah, I look forward to future to see what happens in that front.
I mean, so growing up as a child, I have read many comic books, and I mean, it's amazing to see that those comic books are now being transformed in movies, right? Marvel, right? I mean, do you watch this movie or read such comics?
I am not so much into comics. I have seen the Marvel movies, not all of them, but a lot of them.
I mean, because of peer pressure or just because you wanted to?
Well, neither. They are good fun.
Ah, right. Wow. Okay. I'm just glad you gave that answer. Because I was expecting you would say, no, I did it under peer pressure, but I liked them. But you did for fun, right? That's great.
Who doesn't like a fantasy?
Absolutely. Yeah.
One question I'd like to add on.
Sure.
I mean, when we talk about scientists or people who study a lot, astronomers, the first thing that comes to mind is like a nerdy person, just like into the books all the time. So breaking that stereotype, I mean, I would like to know what are the hobbies that you like pursue, or just barring all this education, all this research work, what are the hobbies that you have just to break the stereotype of being a nerdy person?
I am very glad that you asked that question, because I also very much had that stereotype. And the most interesting people I met belong to the academic field. Oh, as to myself, I am not a very interesting person, but I have some hobbies. Like I'd like to travel a lot. So whenever I get some time, I go on solo traveling to various places. I'm interested in history, a lot of art and architecture. So I go to places that has those kind of things. And have some
How
fun.
can you say you're not an interesting person? I mean, you travel solo. That is like the only thing that makes you an interesting person.
Pranjali, are you making notes? Because I am. I am making notes. What I have to do to be interesting, I'm going to travel from now on.
Making notes.
Good. Actually, being in academia actually is a good thing for travelers, because I used to find conferences and other things like visits and so on to go to really new places. Those were a good excuse to go to new places. You get to do science, you get to see places,
Yeah,
you
you
get to see
also get to
art.
travel. Yeah.
You get to travel.
That was the questions we put in some extra questions also, and it was really any other question, Ansha, I would really like you to ask the question right now.
I mean, I'm really enjoying this interview. I don't know about Manoneeta ma'am, but I'm really having a blast.
I enjoyed it a lot too. And your questions are very, not ordinary, like not the usual ones. So that's a very pleasure to have.
Our purpose is served.
Oh my
Thank
God.
you so much. Thank you so much for finding time for this interview, ma'am. I mean, you were not feeling well, but still you came. So
sorry
thanks
for
again.
postponing it.
No, no worries at all. No worries at all.
We got more time to like prepare for it. We weren't prepared that well.
And I just wanted to know, I mean, how many countries have you traveled?
Well, quite a few. I don't remember the number, but yeah, mainly in Europe.
Wow.
No, not that many. I just don't remember them.
Now you don't remember the number. That means the number has to be large over.
No, not that many. But yeah, I mean, it's not just about countries. I mean, even in India, there are lots of interesting places to go. Just need to.
Yeah, that's what I usually say. Cover up things when my friends ask where have I been. I say India is a good place. I've been to many places.
Okay, man. So without taking like too much of your time, I mean, we could talk like all day long if you allow us to.
It is a very exciting session for me as well. And don't let academics talk; they will not stop.
I mean, all these things are fun. I mean, talking to teachers, taking interviews. I mean, doing something, writing articles. Like, these things really help.
By the way, I really appreciate that effort that you are doing, trying to bring this into the forefront. So these are very important things, and particularly to encourage and show the path to young minds. So I really appreciate that.
Thank you.
I mean, I didn't like had access to like these detailed interviews when I was in school. Like just came right here.
Yeah.
And I'm just glad that we have some amazing teachers who are ready to, give interviews, because not everyone is that polite and that humble and that ready to, talk to students. And I'm glad that department is the best, definitely. And I have heard that from other departments as well. Right?
That's nice.
The astronomy teachers are the best. I mean, you could go to them, talk to them. Right? So that's amazing review that I've got. Even before I entered.
Very happy to get that.
Okay, ma'am. Thank you so much for being a guest of this event. Thank you so much for coming. Okay, so we'd like to end this session over here. Bye bye, everyone. Thank you again.